Okay, here is the mind map for Year 9 Science on atoms and bonding. You can take a picture of the mind map now if you would like the whole picture. Otherwise, we're going to zoom in and have a quick chat. Right, so we zoom in. My idea is that you will follow along reading the various bits of information with or without my voice. So up the top here we have a classical diagram of an atom with the neutrons and protons inside the nucleus, and around the outside we've got electrons in their electron shells. Okay, protons and neutrons have a mass of 1, electrons have next to no mass, but protons have a charge of +1 and neutrons have a charge of neutrality. Okay, when we look over here, this is the sort of symbol you might get for a generic atom. And it gives you the mass number, which is the number of neutrons and protons. And then down the bottom here, we've got just the number of protons. Therefore, the number down the bottom, taken away from the number at the top, will give you the number of neutrons. In a neutral atom, the number of electrons will be the same as the number of protons. Okay. The electrons, when they fill, will fill according to the rule 2-8-8-2, and they will fill in that order. You'll fill up the first shell with 2, then they'll move on to the second shell, and when that's full of another 8, we can then move on to the third shell, and when that's full of another 8, we can then finish off with another 2, and that gives us the first 20 elements. Okay, we go down to what an isotope is. An isotope is exactly the same element, but it has a different number of neutrons, so it's heavier. So if we look over here, we've got an isotope of potassium. We've got potassium-39 and potassium-40. They've both got 19 protons, so it must be both potassium, but this one is heavier. All right, and they're just isotopes of exactly the same element. Then we come up against ions. Now, an ion isn't a balanced particle. It's a particle that has changed its numbers of electrons. Now, before it used to be neutral and used to have equal number of protons and equal number of electrons, but now with the addition or removal of electrons, the charge overall changes. Now, metals, being group 1, 2, or 3, have only a few valence electrons. And by getting rid of those outer electrons, they've got a full outer shell below. But by getting rid of electrons, they end up with a positive charge, and we call them cations. In the same regard, if we've got some non-metals love to receive electrons, and because they've got now more electrons than protons, they end up with a negative charge, and we call these anions. The periodic table is the division of all the matter that we know about. Right, it's arranged according to the number of protons each element has, and the separation between metals and non-metals I like to teach as stepping over aluminium. Aluminium is a metal, so everything to the left of aluminium is a metal, and everything to the right of those stairs is a non-metal. Now, the groups are the columns, and the columns tell you the number of valence electrons, and a valence electron are the electrons in the outer shell. So the groups define the characteristics of the element. Group 1 is called alkali metals. Group 2 is called alkali earth metals. Group 7 is called the halogens, and Group 8 are called the noble gases. Then we come to the periods. The periods are the rows, or the numbers of electron shells. So if you're in the first row, being hydrogen and helium, you've only got one shell that can fit up to 2 electrons. Then the next row down, you have 2 electron shells. Now the next row down, you've got 3 electron shells, and then the fourth row down, you've got 4 electron shells, and so on. The idea of electronegativity is just the relationship between the distance between the nucleus and the electrons are moving around in the electron shells. So some elements like fluorine has a very high electronegativity and is able to rip the electrons off anything that's passing by. And at the same time, if we look down the other side of the periodic table down to francium, we can see that francium's nucleus is very far away from its outer electrons, and so it freely gives away its electrons because it has a low electronegativity. All right, next we move on to the different types of bonding. Okay, so the first major type is called ionic bonding. It's between metals and nonmetals. And we say that there's an electrostatic attraction between the positive cation and the negative anion. And in the ionic compound, we get an overall neutral charge because we should be getting the same number of positive charges with the same number of negative charges. The rules for balancing equations, or ionic formula, we should say, I stick with these three rules. If the numbers on the charges are the same, so sodium is +1, chloride is -1, 1 and 1 are the same number, we just do nothing, we just smash them together. If the numbers are different, so we've got a +2 and maybe a -1, if we get a +2 of magnesium and a -1 of chloride, we do swap and drop. So the number 1 from the chloride goes across to the magnesium, and the 2 from the magnesium goes across to the chloride, and so we end up with MgCl2. And then my third rule is if the cation is +4 and the anion is -2, rather than it being cation 2, anion 4, it just gets truncated into cation, anion 2. So if I had lead 4, which is lead 4 plus, and oxygen, which is 2 minus, instead of being Pb2O4, it just becomes PbO2, or lead oxide. The properties of ionic compounds is that they form a crystalline structure that is very hard but brittle. They have a very high melting and boiling point due to the very strong bonds. It conducts electricity when it's aqueous, which means dissolved in water, or molten, which just means melted, but not as a solid, and they are soluble in water. Now, covalent compounds is where you've got the bonding of 2 or more non-metals. Here they share electrons. Okay, and then we have, if the word allotrope means a different form of exactly the same element, and the one we teach here at this school is carbon. We have one form which is a buckyball, we have another form which is pure carbon, which is a diamond, and we have another form which is pure carbon, which is a diamond. Okay, rules for balancing covalent compounds, where they all must attain a full outer shell, and any unpaired electron can be used in a covalent bond. When naming them, prefixes matter, so mono means 1, di means 2, tri means 3, and tetra means 4. The word water, if it was to be put into a covalent compound, would be dihydrogen monoxide, as in 2 hydrogens and 1 oxygen. Okay, then we come to properties of covalent compounds. Now, there are 3 major types of covalent compound. We'll just zoom in a little bit. The first one is what we call covalent molecular, sometimes called simple molecular. It's where 2 atoms will share their valence electrons. And remember, a valence electron is an outer shell electron. And so we just overlap those outer electron shells. Where they share 1 pair of electrons, that's a single covalent bond. Where they share 2 unpaired electrons, that's a double covalent bond. And in something like nitrogen, they'll share 3 unpaired electrons, and that would be a triple covalent bond. Okay, covalent bonds are poor conductors because the electrons are all held up in bonds. Right? They have a very low melting point and a low boiling point because these molecules, although they're very hard inside, they've got very weak bonds between them. And when those weak bonds are broken, what we call the intermolecular bonds, the individual molecules are able to separate. Right, next up we have a 3D covalent network, which is a diamond. In a diamond, each carbon is covalently bonded to 4 other carbon atoms. This gives it a very, very high melting point. In fact, it doesn't go through a liquid phase, it just sublimes, goes straight into gas. It's very hard because the bonds are very, very strong, but a poor conductor because there are no free electrons hanging around. On the other hand, we've got 2D covalent networks like graphite. Each carbon atom in graphite is only bonded to 3 others, which means the 4th electron is floating around either on the layer or between the layers. So it has a high melting point, but is brittle because it shears off in those layers. Here we can see the layers. It is also a very good conductor of electricity due to those free electrons, whereas a diamond is an insulator. It cannot conduct electricity. Okay, then we get to metallic bonding, and metallic bonding is between 2 or more metals. If it's more than 2 metal, or more, if it's more than 1 metal, be 2 or more metals, we call it an alloy. All right, the outer valence electrons are shared evenly amongst the cations, and we say that it is a lattice of metal cations in a sea of delocalized electrons. And the word delocalized electrons means these little blue dots which the electrons are able to move around freely, which gives it its great properties of conducting electricity, because if you throw on an electron at this side, it will jump off in another direction. A very, very good conductor of electricity. It's malleable, which means that as you bend it, the electrons and the cations can just move around into a different formation. Okay, so in summary, we have this lovely table showing you the characteristics of the different types of bonding. Okay, now if I move out again, I'll give you the full view. You can take a picture of that. Thank you for listening, and I hope you've learned something from this mind map. Goodbye.